this is question 4 of the midterm. Okay, so let's get started. In box 4a, draw the HOMO, which is the highest occupied molecular orbital of the allyl anion. Okay, so let's start by drawing the pi molecular orbitals on each of these. Since this is an anion, it's also got one on the last carbon. So each one of these would have one. And as you can see, there is no double bond here, but there is a lone pair, which would account for the negative charge. And that would mean there are 2 electrons on this third carbon, if we were to name them 1, 2, and 3. Okay, so that gives us 4 electrons in total with 3 pi orbitals. Now we want to draw the molecular orbitals for each one. So since we have 3, let's start by throwing 888, which is 3 orbitals, and you can just shape them in. And then as you can see, there's 0 nodes in the lowest energy. Okay, let me just label that. All right, okay. And the highest one would have 2 full nodes in the middle. Okay, and the middle one would need 1 node. And how do we get 1 node? We have to not include one of the orbitals. And that would be like multiplying it by 0, which we covered in the lecture. But the simple way to look at it is that this is the only way we can have 1 node between 3 orbitals. So there's that. Okay, so let me get rid of this because we're gonna need that space. So these are the lines for the electrons. So we have 4, and as we know from before, each orbital gets 2. Okay, so this is occupied. So this is the highest occupied molecular orbital. This one is unoccupied, making it the lowest unoccupied molecular orbital. The question is asking for us to draw this guy, and this is what you would draw in box 4a. Okay, so in box 4b, draw the isomer of C5H8 with conjugated pi systems. Alright, so this one was fun to do, at least in my opinion. Well, more fun than the other questions because none of this was fun. So we want to find the degree of unsaturation at first. That's the first thing we always want to do when we look at something like this. So that is 2C plus 2 minus H. And there's some other stuff, but since we don't have anything but C and H, this is all we need, divided by 2. And this also applies to the next question, so that's good for us. We only have to do this once. So 2 times 5 plus 2 minus 8 divided by 2. Okay, so that's 10 plus 2 is 12 minus 8 is 4 divided by 2 is 2. So there's 2 pi bonds that could be either 1 triple bond or 2 double bonds. We can't have any, or it could also be one ring and combination of a ring and pi bonds, but we can't have any benzene rings because we need at least 4 degrees of unsaturation for that. So 2, let's work with that. Okay, so since we have 5 carbons, the easiest way to start would be just to draw. Okay, so let me draw a line. This will be 4B and this will be 4C. So the easiest way to start would be just to draw 5 carbons. These are 5 carbons. So we want 8 hydrogens. And we have 2 degrees of unsaturation. We could have a ring, but we'll get to that later. Let's see where this goes first. And we want, I forgot to already mention this, but we definitely want a conjugated pi system. So if we were to draw just double bonds here, 2 double bonds, this would be our first isomer that we would do, even if we're just doing a guess and check method. So let me just change color. This one would have 2 hydrogens. This guy would have 1, 1, 1, and then 3. So what does that give us in total? That's 2, 3, 4, 5, 6, 7, 8. That is both 5 carbon and 8 hydrogen. That satisfies it. But is it a conjugated pi system? Yes, it is, because these guys right here, these 4 guys, are all in conjugation, and we can have as many resonances as possible, and each one with a pi electron. This is an sp3 hybridized, so that is not part of the conjugated system, but these 4 carbons are, and that gives us a conjugated pi molecule. There's no other way to do this with a ring, because then you'd only have 1 double bond, because that would mean a ring would leave you with 1 degree of unsaturation, and then you can't have a conjugated system with 1 degree of unsaturation, because you'd need at least 2 double bonds to have a conjugated system. I hope that makes sense. Okay, so for 4C, it's asking for the same thing, but with a cumulated pi system now. And already we can draw this guy. This is basically all we've seen for cumulative pi systems, where this molecule is sp hybridized and these 2 are sp2 hybridized. Just for space, let me just do that. But we already know that DOU was 2. Okay, so that accounts for 3 carbons, and if we were to draw the hydrogens, this would have 2. This would have 0, because 1, 2, 3, 4 bonds are already on carbon, so we can't have any hydrogen, and we want to add more to this side right here. So that's 3, 4, 5. Okay, let's see if that works. If it doesn't, then we might have to change one of these bonds and put it on that side. All right, let's go back to red. So this one, since it has 3 bonds, will have 1. This one will have 2. This one gets 3. So that's 1, 2, 3, 4, 5, 6, 7, 8. That works out perfectly. So if you were to just clean this question up a bit, that would be your molecule, and right here is the cumulated system. Okay, so that's your answer to 4C. So in box 4D, draw the resonance hybrid of this molecule. Let's do that. So this is one of those questions where you have to draw every single resonance structure possible. Yes, it is tedious, but apparently this is important, so let's just get on with it. So you can start by just drawing the basic, like the backbone of the whole thing, and then you can just push arrows on here. Oxygen can't move this the opposite direction, or oxygen has to, let me just say, it has to move in that direction, because otherwise we'll have an empty orbital on the octet, so we don't want that. So this would give this molecule with 3 lone pairs, which would make oxygen negative, and this carbon positive. Benzene would stay intact. So that's one. Okay. Next, we just want to like push the benzene arrows and just cover all the resonances that benzene can go through. There are usually 3, and after I'll show you something that can help us do this faster. So that would make the double bond go here, and this, and this, and just move the positive charge there. Let me just okay, so we want to push this right here just to change the location of the positive bond. That's basically all we're doing at this point in essence, and just everything stays exactly the same except where we've pushed arrows. That would make this positive, and the next one is just basically the next in line. Okay, so, and then if we were to just move this here, no, sorry, not there, this here and this down, it would give us the original molecule. Okay, so we see, so to draw the resonance hybrid, we want to draw the single bond backbone of the molecule, and then, as we know that benzene always has full conjugated system because that's the nature of an aromatic ring, and the pi bond extends over here onto the oxygen. Okay, so now we want to assign partial charges. Oxygen has seen a negative charge through the whole thing, so it's got a big partial negative. It doesn't have a full negative because in the original molecule it is neutral with 2 lone pairs. So you can't just put a negative charge, it has to be a partial negative. And then for the positive charges, let me just do this in red, there would be a small one at every molecule that was positive. So starting with this one, and then over here, or every atom that was positive, and then one right here, and the last one will be right here. So that is the answer to 4D. But here's another quick shortcut that usually works, but don't like quote me on this, because sometimes it might not, when you, especially when you have like an odd numbered ring. It works in an even numbered ring, but every second carbon on the benzene ring would have a positive charge. So if you find one positive charge, let's say we found this one, so you can always just skip a carbon and then go to the one after that, and that would have a positive charge in resonance structures like this. It takes a long time to draw all these resonance structures, so if you're short on time, just consider this. But if you aren't short on time, it does pay off to do the whole thing, and just in case you don't make any mistakes. And this one as well, sorry, this one as well is a second carbon, which means you're skipping this one and then you're just going to this one, and it's also got a positive charge. That would also apply to like allylic stuff like that, but that's not what we're talking about. This is the answer, and yeah, that's this question. Thanks for watching.